Hi guys, so I'm going to try and make this quick today. We're going to go through an example of how you could answer the questions, find out some of the information regarding the unique data you've been sent for your resistor capacitor. So we remember that you have got a simulated series RC circuit. You were given the capacitance and you weren't told the resistance. So you've got to use the something relating to how the signal is charging up to determine what's going on in your system. So I'm going to work through with someone's data, someone who I know has already solved this. So I can go through and I know that their resistance was 360 kilo ohms. So the very first thing I'm going to do is import NumPy as NP, and then I'm going to load their data file up. I've got all of your data files on my computer, so I'm going to load it up. I hope I'm not, I'm just going to have to release someone's ID number here, but it shouldn't matter. You've all got access to those numbers anyway. Okay, so I've saved these all in a subdirectory called data files. So I'm going to say that my individual data file is an F string in this subdirectory data files, and they're all called RC charging underscore, and then I'm going to put that student ID there. So the first thing we want to do is we want to take that data and import it and see what it looks like. So I'm going to do all data is equal to numpy.gen from txt data file. Let's see what this looks like. I don't think this will work, but what does it give me? Doesn't like it because it didn't find that because it's a .csv. Let's try and run that. Doesn't like it because they are not numbers, because I haven't told it some more information it needs to know. So I'm going to say that the delimiter is a comma. Let's see if this works. Delim. How do I spell delimiter? Let me think. There we go. It's not delimeter. It's not a. It's not a measurement device for a delicatessen. It's a delimiter. Okay, so I've got all of this data in here now. I could also tell it to skip the header rows. Let's do that as well. So some of you might have trouble with your headers. Let's tell it to skip the headers. There we go. So we've got three data constructs now. We've got let me just move this so I can see where I'm pointing on screen. Okay, so we've got time, and we've got the voltage that's input, so the charging voltage, and we've got the capacitor voltage. So we've got those as names, so let's take those out and do something with them. Let's say so time is the first one, V in is the second one, and VC is the third one. So the very first thing we can do is we can just plot these data and see what they look like. So we're going to do imports matplotlib dot pyplots as PLT, and then I'm going to do %. I'm going to do matplotlib notebook, and this is what enables us to zoom in on graphs. So I'm going to make I've run that cell, I didn't mean to. Let's do plt.figure, which is going to make us a new figure, and then I'm just going to plot those two separate bits of data. So I'll do plt.plot time vin. I'd like that to be a blue line, and plt.plot time vc. Let's make that a red line. Let's see what happens. Why isn't that running? Oh, it's because this is an uppercase VC up here, and I wanted to plot lowercase vc. Okay, so we've now got our graph. This is our RC charging circuit. So this goes from 0 to just over 6 seconds. And if I click on this one here, it enables me to zoom in wherever I'd like. So let's say we would like to look at this bit here. There we go. I'm going to say let's look at one cycle. So we'd like to go from 0 to about 0.3. Let's have a look at that. So I can tell the axes to be changed to that. So the PLT, let's use PLT to do that. PLT, I'm going to get the current axis, which is a method of PLT, and I want to set my X limit to go from 0 to 0.3. So now if I run this again, there we go. This is my RC charging circuit. So we can see this first one here it was charged and then discharged, and then up here it starts charging again. So we could use this and we can do sort of a rough and ready estimate of what the time constant is on this circuit. Let's do it the rough and ready way. So let's see if I can get a good estimate for this will give us, this is the sort of easy and cheeky and cheap way of doing it. We can see on here that I gave you nice integer values for your up and down frequency, sorry, for the VN frequency. So it's going to be plus 12 to minus 12. So we can write this down. So it's 24 volts peak to peak. So let's say, remember when we're looking for the time of the charging circuit, we can sort of ignore the numbers along the bottom or their absolute values, because all that the RC circuit knows is that at this time here, it's starting charging. So this time when it's been switching from being minus 12 volts to plus 12 volts, we want to know what this time is. So I've put my cursor on here and I can see along the bottom, it tells me the size of that rectangle it's been zoomed into. So I can use that to then write those numbers down. So it's hard to do this and do everything else on screen at the same time, but there we go. So that tells me here that let's call this T0 is equal to 0.149 seconds. And let's just zoom out again so I can click home. Let's choose a point on the graph somewhere up here. So let's zoom in here. Okay, let's say T1 is 0.162 seconds. And then the value of the voltage here is the y-axis here. So this is V1 is equal to 9.206 volts. Those values I've got here. So I can use these values to work out what my time constant is. This is a lazy way of doing it, but I'm going to show you how we do it anyway to do the theory, and then we're going to code it up. So I've got these values now. This is enough to work out the time constant. So what I want to do is use these values and do a quick calculation based upon it. So let's write this down here. Let's call it the inelegant calculation. So T0 is equal to 0.149. We'll say this is the start of charging. T1 is equal to 0.162, where we sampled. And then we'll say that V1 is equal to 9.206, which are these numbers we wrote down here. So I can get rid of those now. What I can now do is I can use these values to work out my time constant. So the value up here was about 9.206, but the capacitor is charged from minus 12 up to that. So that tells me that my capacitor voltage is actually 12 plus this value. So VC in uppercase. So I'm going to say VC is equal to 12 plus 9.206. That's going to give me the value of the capacitor voltage. And I'm then going to say that my T, or let's just call it T, time is then the time taken from here up to that point. So that's just T1 minus T0. Okay, so we can then remember our capacitor charging circuit. Let me just check I'm writing on screen for this. So we've got VC is equal to V in 1 minus e to the minus t on tau. So the unknown thing that we want is tau. So 1 minus e to the minus t on tau is equal to Vc on V in. So if I rearrange this, I'm going to end up with minus t on tau is equal to the natural logarithm of 1 minus Vc on Vn. So therefore, tau is equal to minus whatever the time difference is, which we know, divided by the natural logarithm of 1 minus Vc on Vn. So the values that we've got in here, we need to think about. T is the difference between T0 and T1, so T1 minus T0. Vn, this is the peak-to-peak voltage that we're charging with, so it's going to be 24 volts, and this value here is going to be the 12 plus 9.20, whatever it was. It's written up here, 206. So we can do this calculation now. We can calculate tau. Tau est is equal to minus t divided by the natural logarithm, mp.log, 1 minus Vc divided by 24. Okay, so a small number here. Let's import SI format to help us do this. Let's say from SI form prefix, import SI format. Let's give us 3 degrees of precision. There we go. Estimated time constant is 6.045 microseconds. Now this person had a capacitor of 17 microfarads. R is simply going to be tau est divided by 17 times 10 to the minus 6, so we can then estimate the resistor. And I can actually just find an omega somewhere. Let's do, oh no, don't you see that? You can see this, that's fine. So let's go to omega symbol. Let's search for that. I'm going to have to go back and check this video because you might be able to see my Slack private key if I share that with you, and that would not be good. Bingo. Okay, so on here, we've got, using this sort of rough and ready method, estimated resistor is 355.50. That's a silly level of precision to have in here. 356 ohms. Now I said I know this one is 360s. That's pretty damn close. So let's see if there's a smarter way of doing this, using something more slightly programmatically. So let's see if we can figure this out. I haven't done this before, so let's give this a go. Method 2, let's be smart. So we want to take a look at our signal and see if we can work out repeatedly over all of these cycles, if we can work out what the time constant is. I would recommend trying to find out where the 63 point whatever it is value is that we know one time constant is. And then we can, from that, work out what the resistance is. Or rather, let me just sketch this out. So if we were to take some position on our RC charging circuit, if we were to somehow recognize everywhere where we start charging and everywhere where we start discharging, then we can use that to say, okay, every time we find one of these, find the next point where the voltage is equal to 63.5% of the total V in. And obviously we're not going to use 63.5, we're going to use the actual value based upon the equations that govern the RC circuit. So let's see if we can do that by playing around with this. So bugger. So after all of that, I just talked through how to do this and realized I hadn't switched it over to the screen. So let's make sure I go through this properly now. Bugger. So what I've redone here is I've just replotted out the whole array. And what I want to know is the indices of when it starts to charge. So if I was to plot out Vn, if I was to write out Vn, I could see for this circuit it's going to be something like 12, 12, and then it's suddenly go to minus 12, minus 12, minus 12, 12, 12. Obviously, there'll be hundreds of these values, not just a couple. And so what I can see that if I was looking at the difference in each of these, so then if this was Vn n plus 1 minus Vn n, 0, this would then suddenly jump to minus 24, 0, 0, 24, 0, 0, minus 24, 0, 0. So the values that I want is this one, when it's a big positive number. Because this is simulated data, there's always going to be nice numbers. I haven't put any noise in here. If this was a real RC charging circuit, then if you zoomed in on here, you'd actually see this would be a slightly noisy signal. So you would maybe expect this to be like 12.12, 12.01, minus 12.13 or so. So we'd have to just look for when the difference between two values is maybe, say, greater than 95% of VPP in, for example. Okay, I'm showing you that we're using a method here that you'd have to be slightly careful with using on real data, just being smart about how it's going to be applied. So what we need to do here now is we need to say, I want to look for the index. Handily, if you were an undergraduate student, you might think, okay, well, I'm going to write a loop to do this. I'm going to iterate over all of the objects in, all of the items in my array, and I'll just do an if it's bigger than a certain amount, then I'll put that in a new array. That's not a very good way of doing things in Python or in MATLAB. So we're going to make a Boolean array. So we'll say find where the charging points are. So I'll say my Boolean index of where it starts charging is equal to wherever the difference of Vn is greater than 0. So that's then told me all the points where those differences, effectively it's found all of those points here, the leading edge of the bottoms of these. So there are some trues in the middle here, they're just not shown. We don't really care about the Boolean indices because that's going to be false, 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 true, false, 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 true. What we want to know is where they occur. So I'll say the indices of where it starts charging is equal to np.where of the Boolean. And then if I print this out, okay, it's given me an array out. It's actually giving me a tuple with an array and then nothing after it. So to stop that being a tuple, I say of that tuple, I only want the first elements. And then got the index of where I start charging now, which is handy. So what I can now do is I can then use these indices to plot those charging points on the plot just to check I've got it correct. So let's say plot and check. I'm going to say plt.plot time. Interesting, and this will work whether you use the Boolean or the index in here, it doesn't matter. I just like to use the indexes because they make more sense for you to look at as a human being. Moment of truth. There we go. So what this has done, it's found the points at which those charging cycles occur. So we now know that we've got all of those charging cycles and we're able to see where they all occur, which is handy. So what I'm now going to do is say from the first one to the second one, let's zoom out a sec. So what we're now going to do is go through a loop of this vector and say, let's zoom in. It's going to allow me. So what we can do now, we've got this graph. Let's sort of draw this over here. This is what I mentioned in class about the time vector and being careful with it. What we want to do is, now that we know where this value is at the beginning, we want to, this could be, let's say this t equals, it could be 1,000,000 seconds. It doesn't matter what it is. It's just a number. It could be, 7 seconds. What we want to make sure is that in this next bit of data, let's just draw a little bit up here as well. We would like to say that we're really not picking the right color here. So we're going to say that for every piece of data that is within here, we want to, in fact, I'm going to have to do a little bit of extra logic because I'm going to want to find out where the top is up here actually, because I don't want this data. I want just this data here. Okay, so we're going to have to extract that. So we need to work out where this leading edge is up here. I just realized the way I want to solve this won't work if I have all of these data in. So let's see if I can bring these out as well. Just going to copy this line down here. Let's the Boolean of the starts discharging. It's exactly the same. I just need to change this to be a less than. And let's plot these on as green squares. And let's keep this zooming on here because this will help me. So I'm going to go up here and copy that bit of code I had up here. I'm going to change my axes to go from 0 to 0.7. There we go. Oh, that didn't work. Why didn't that work? Oh, it's because I didn't change what I'm actually plotting here. Let's just say, I'm just showing you I can also put the Boolean indices in here as well to get this to work. I can't actually because I can't use the Boolean indices because if you take the difference of an array, np.diff, it ends up giving you an array that's one shorter than the original array, because all you've done is you've said for each element subtract it from the next one. So the array you get out is one shorter than the other. So you can supply the indices, this still works, but if you supply a Boolean array, it's going to be too short to give this out. But here we have now, we've got a plot that shows the starting points of charging and the ending points of charging. And this is good actually. It's good that it starts with a discharging point. This isn't going to help me because what I want to do is I want to loop through this array. I want to say from the first charging point to the first discharging point, that's going to be the data. But actually my first discharging point is down there. So let's do some logic in here to get rid of that. So let's say remove the first discharging point if it's before the first charging points. So let's say if ind starts so this is saying if the first discharging point is before the first charging point, then we'll say get rid of it. So we'll say take that vector. Oh, sorry, that should be zeros in here because I want to say look at the first ones. I'm then going to say take this vector and make it equal to what it was before, but instead we're going to start at the second entry and then all the way to the end. Now if I run this, that didn't work. Why didn't that work? If the index starts discharging. Oh, I know why. It did work, but I plotted it before I removed it. So let me remove that bit up here. Do this here. There we go. And I'm actually going to do the same, but the other way around. So I'm going to say if we get to the end of this and the last point isn't a discharging point, so let's just zoom out on here and just see if it's going to be an issue. So let's replot this. So yeah, because my last point is a charging point, I would like it to go from charging to discharging, and then ending on a green point. So I now need the code to say if the index of starts discharging endpoint is greater than the last. Nope, let's make it that way around. If the index of the starting discharging point is less than the last charging point, then I want to make sure that the index to start charging, I need to get rid of the last charging points. There we go. So I got rid of that last point on here. So now what I can do is I can go from, say, from every charging point to every discharging point. I can then extract those bits of data and do something with it. So I'm going to say, let's iterate over the charging and discharging. So we'll say for, now I'm going to write a loop and then we're going to think about what it says. So for I, comma, I start, I end in enumerate zip. So what this object is saying, okay, is that 1, 2? This is saying it's going to loop through, and this is probably the easiest way to show you. I'll do print iteration I starts at so this is just a loop that iterates over those start charging points and then has the values of all of these three things. It tells me which iteration number we're on, what our start charging point and what our start discharging point is. Won't work because there's no such thing called enumerate. It is a numerate. There we go. Oh, that doesn't like that. Oh, this is why, because I tell it to call the output from these two things and then I don't use them. So these should belong in there. There we go. Iteration, the first iteration starts at 1075 and ends at this one here. So this now tells me I can then select those parts of this time vector and the VC vector and do some operations on them. So let's just think about what I want to do with those data. So I'm going to want to find out some information about let's just say I've got one of these. So if I can now get all of these data, I can have, this can be my T0, This is just the end, so I then have all of these data in here, and I'm going to have time, and I've got VC, and I'm going to work on those two things. So I can say that I want to subtract T0 from each of those, so we'll call this T is equal to time, which is a vector, minus T0, and this then tells me the time it's been charging from. Because remember, this is my y-axis, or my x-axis down here, this is just increasing time. So this is just an arbitrary value here. Could be 5 seconds, could be a million seconds, could be 2 hours. Doesn't matter to the RC circuit. All that matters is the time elapsed since this point. And I'm going to want to find the time it takes me to go to one time constant. So that was 63 point something. We'll work out what that value is. And we're going to know what that is because it's going to be that percentage of this total, which is 24 volts. So we're going to then work out where along this curve this occurs. And what I'm going to do that's a little bit smart, or at least I think is smart, is I'm going to make an interpolant. I know if I was to look at this curve, I could then work out what the time is as a function of the voltage, and then I can make some sort of fit between those two things. And then I'm going to put this value, 63 or 0.63 multiplied by 24 volts into here. Okay, 64 multiplied by 24 volts minus 12 volts because it starts off down here. Okay, so I want to know when it gets to this value here. So let's go back to the code. I'll remember to put it up this time so I don't have to do too much video editing. So let's go through each of these and find out. So we'll say get our time vector out, extract the time vector. So T is equal to time I start to I end. This actually doesn't include the endpoint, but we don't care because it's fully charged by then, minus that first value. This is then my time vector for each of these, and I want to extract the VC vector. So VC, I'm going to call it uppercase VC is equal to VC I start to I end. Now we're going to do an interpolant here, so I need to import something from SciPy. Import SciPy and import SciPy.interpolate. So I'm then going to make a 1D interpolant, and this is going to be time is equal to SciPy.interpolate.interp1D, and then I'm going to say I want to know my x, or my input is going to be VC, and my output is going to be the time, which is this new time vector along here. So this is then created an interpolant. I can then put a voltage value in, and it'll tell me how long it'll take to occur at that value. So before all of this, I need to work out my value at 63%. So my value at 63, more my value after one time constant. So let's say time to 1 tau. Sorry, not time to 1 tau. So we'll say voltage at 1 tau is equal to minus 12 plus 24 times 1 minus np.exp minus 1. Let's print this out here actually. Print okay. Oh, that's clearly not correct. Voltage at one time constant should be 182. Why isn't that right? Or minus. Oh, because I'm minus 12 multiplied by 24. minus 12 plus 24. There we go. So this says a one-time constant, we should have a voltage of 3.16 and a whole bunch of stuff volts, which let's go up. Yeah, that looks like about 63%. I'm pretty happy with that. So I can then feed this value into my interpolant that I've made here. So let's say find the time this occurs at. And then this value will be one time constant. So let's say 1 tau est is equal to time interpolant voltage. Let's copy this in. Bloody hope this works now. There we go. I've got two versions of this. Let's get rid of that. Okay, estimated time constant 6.1 microseconds. Sorry, milliseconds. So I've got a consistent time constant here, which is pretty cool. I've misspelled constant, but that doesn't matter. Let's see if we can get the resistance out of this. So if I want to find the resistance, so remember it's 16 microfarads was the capacitance for this guy's resistor. Won't be the same for yours. We'll say R is equal to 1 tau est divided by C. Print hence the time constant. No, sorry, hence the resistance is let's get that omega symbol from up here that I used. Remember, we got 356 here. I've got an order of magnitude wrong somewhere in here. This is order of magnitude wrong somewhere up here, I think. So I know it's actually 360 kiloohms is the correct value. Let me just figure out where on earth I've made this mistake. I think the mistake's up here somewhere. That's weird. I'm getting the 6.1 milliseconds here. I'm getting very similar here. I'm making some stupid mistake here that I can't figure out. So SI format of R. I think something happens with this SI format here because I just printed out the value of 1 tau estimated here, and it's, let's just take this value out. Yeah, something happens with this SI format that actually changes the value of that. Let me just try something else here. That's weird. Yeah, I can see what's happened here. So the value is, the correct value is 360 ohms. I was wrong earlier, and I've just checked in the notes. The correct value is 160 ohms, and you confirm, so 360, which is pretty much what we're getting up here. So this value is correct. Something is occurring down here. Let's just put this line back in. That's using SI format in here is actually doing an operation on 1 tau estimated that removes its, let's just do a help on SI format, see if I'm using that correctly. It's almost doing an in-place change on it that I don't want it to be doing. So if I now just move this line down here, yeah, there we go, that works. So that was annoying, but I got to the bottom of it, and I think it's important to show you guys when I make mistakes and can realize it. Every cycle here, it gets the resistance being 360. So I don't need to bother averaging it. Again, this was fake data, so it's going to be consistent as we go through. Two different ways of doing this. Top one up here, using the hand or the inelegant calculation. Second way was using this smarter means of doing it. So hopefully you've learned something from this. If you've already coded it up and did it using some sort of loop, then have a look at the way that I've done it, see if you think it's better. If you think your way's better, then let me know. Then give me a message about it and show me. I'm going to edit this to make sure that I don't include different things in it, and I will see you all in class next week.